So let's start our afternoon session. The first afternoon speaker is Alexander Molev from University of Sydney. He will talk about quantum Casimir elements and Sugawara operators.
Thank you very much. I'd like to thank the organizers for inviting me. It's a great honor to be in this institution. So what I'm going to speak about is motivated by something Naihuan already mentioned in his talk. Just to understand quantum versions of some classical objects like Casimir elements. What are quantum Casimir elements or quantum Sugawara operators? So that out of this motivation we'll need to consider quantum groups instead of Lie algebras. And that topic, of course, appeared in this form I'm going to speak about, appeared in the 80s, beginning of 90s, where many new objects appeared, but many questions still remain. And I'm going to give some answers to some of those open questions. So to start with something everyone familiar with, I'll start with representations of GLN, then going to our first result, calculating of eigenvalues of Reshetikhin, Takhtadzhyan, and Faddeev central elements. Then consider q-immanents, similar to what Naihuan considered, but they're different. So I'll explain that in a moment. And then we'll talk about Sugawara operators and a quantum version. So this is based on our work with Naihuan and Ming from Guangzhou. This already published in 3 papers quite recently. So first thing to recall is the Harishchandra isomorphism. We think of GLN, just general linear algebra, and consider its universal enveloping. That defining relations have already appeared in Natasha's talk. But we think of this as an associative algebra. I use capital E to distinguish the elements from matrix units. Then any element of the center of the enveloping algebra is called a Casimir element. That's the terminology I use. Now, for any n-tuple of complex numbers, we can introduce the corresponding highest weight representation. So call it L of lambda. Say, suppose it's irreducible. And it's generated by a non-zero vector psi, the highest vector, which is annihilated by all upper triangular generators, and is eigenvector for diagonal generators with eigenvalues given by lambdas. That is the L of lambda. Now, every element of the center will act in this module as a scalar multiplication. Multiplies every vector by a scalar. Scale is chi of z. Now we'll take this chi of z and we'll think of chi of z as a function of lambda. So let z be fixed, but lambda will vary. Then this is going to be a polynomial in lambdas. And moreover, that polynomial is symmetric in the shifted variables, which I call L1 and so on Ln. So shift by n minus I, this is shift by rho if you think of a general theory of root systems. And in this way, we'll get a what's called the Harishchandra isomorphism between the center. This map turns out to be an isomorphism between 2 algebras, the center of the enveloping algebra and the algebra of symmetric polynomials. So that result tells us everything about the center as an abstract algebra. So that isomorphism was a motivation for mathematical physicists and representation theorists to understand this from both sides. On the right-hand side, we have the very nice object, just algebra of symmetric polynomials. There are very nice generators, as Natasha already introduced in her talk, like elementary symmetric polynomials, power sums, complete symmetric polynomials, short polynomial, whatever you like. And then you may ask the question, if you take these elements on the right-hand side, what are the corresponding central elements? You can ask this question, or otherwise you just construct your favorite central elements, which you produce from Lie algebra approach. Then you ask the same question, what are the corresponding symmetric polynomials? So this kind of game played for many years, starting from about 1960s, and there are many answers to those questions. I just mentioned one of more recent result by Okounkov, Olshansky. They produce so-called quantum immanents as mu, which form a linear basis. Rather than generators, they form a linear basis if mu is runs over Young diagrams with at most n rows. Then the Harishchandra images turns out to be some polynomials which are closely related to the Schur polynomials, but not exactly to Schur polynomials because they are not homogeneous. This as mu star, if you think of them as functions of lambdas, they call shifted Schur polynomials, but if you think of them as polynomials in else, they are symmetric and known as factorial Schur polynomials containing some low degree terms. So this is one inspiration for us to consider quantum analogues of those objects. What are q-immanents? How can we leave this to quantum group? And in the one particular case, where mu is a column diagram, those quantum immanents become just Capelli determinant. That's the column determinant of this matrix with entries in the enveloping algebra. When we write this as a polynomial in U, there will be some coefficients C1, Cn, and their images of this determinant are easy to find. When you want to find Harishchandra image, you just apply your central element to the highest vector. Therefore, all upper triangular generators will disappear if they are on the right-hand side. And it's very easy to calculate for the column determinant because all elements in the last column disappear. There is only one component, which is product of diagonal entries, which survives. Therefore, the Harishchandra image is immediate, and therefore we get exactly the elementary symmetric polynomials as the images. This is one family of central elements. And another family is given by so-called Gelfand invariants, as they're known in the literature. This probably more well known. We just combine all the generators in the matrix E and by n matrix and take the powers of this matrix, traces of the powers. They were introduced by paper of Gelfand in 1950, and that's why they call Gelfand invariants. Now, this time, to show that these elements are central is very easy. But difficult part is to calculate the Harishchandra images. Going to be some symmetric polynomials, but what are they? They are to be more complicated. And the result was given by Perelomov and Popov 1966. These are explicit formulas for their Harishchandra images. So this which here indicates that zero factor is skipped in the denominator. It looks like a rational function, but this is only an impression. So this is in fact a polynomial, although it's written as a ratio of two polynomials. So the top degree component is power sum symmetric function. Therefore, if we restrict M to the first n values, this will be the generators of the center. Well, the work of Perelomov and Popov relies on a direct computation of the images using inductive procedure, but there is now rather simple proof of those formulas based on this formula here relating the Gelfand invariants with the Capelli determinant. So that simple formula allows us to do this calculation very quickly. That formula here is obtained by using a matrix technique. I will not discuss the proof, but saying just when you want to calculate Harishchandra image, it's easy for the right-hand side. So this is just this rational function. Then you extract polynomial coefficient of u minus m minus 1 in the decomposition. That's just very technical part, and it can be done in this way. So the reason I show you this formula, because that's exactly the approach we want to take for the quantum groups. Now I'm going to move to quantum groups, and the proof will be exactly the same, although I will not be able to discuss it in detail, but the idea is exactly the same. We want to connect two families of central elements. One of them will be quantum determinant, which is similar to the Capelli determinant. The other would be quantum analog of Gelfand invariance. So now let's move to the quantum groups. So I'll remind you what Reshetikhin, Takhtadzhyan, Faddeev presentation is. So in this presentation, we think of UQ of GLN as the algebra generated by the entries of two matrices, L plus, which is upper triangular, and L minus, which is lower triangular. And there are some defining relations. So all of these entries are the generators of our algebra. The defining relations are given as follows. So on the diagonal, L minus, L plus just inverse to each other, and there are these RTT relations. We saw them in Naihuan's talk. Although Naihuan used the full matrix T, that object was a dual Hopf algebra in the sense of Hopf pairing. So in this case, we consider quantum UQ of GLN. So for that reason, we need to consider two parts of the matrix, lower triangular and upper triangular, and R is the same as in his talk. So that's the R matrix satisfying the Yang-Baxter equation. And the notation I use here is explaining these formulas. So we consider auxiliary spaces of endomorphism algebra, and L1 means we could take matrix L living in the first component, L2 living in the second component, and sometimes we need several copies of endomorphism algebra, then we use corresponding subscripts. So that's the algebra, and a closely related object is so-called reflection equation algebra. We can consider full matrix, which is L plus, L minus inverse, call it L. We can think of this as a subalgebra in UQ of GLN, or we can think of this as an abstract algebra, whose generators are entries of L, now full matrix. But because L plus is upper triangular, L minus is lower triangular, the matrix L retains almost all the information about the generators. So therefore, this subalgebra is almost isomorphic to the UQ of GLN. And the defining relations are found easily. That's the matrix R check, which Naihuan also introduced. This one single reflection equation, which defines this algebra. P is the permutation operator. Now, quantum Gelfand invariants, they were introduced in that paper by Reshetikhin, Takhtadzhyan, Faddeev, but they didn't use that terminology. This is our terminology. I don't give it. So the reason is just pure analogy with Gelfand invariants. This just traces of powers of the matrix L, but Q powers. So, sorry, Q traces. Q trace is this usual trace pre-multiplied by a diagonal matrix. That's what I call Q trace. We consider these Q traces of the matrix L, and the result, which pointed out in that paper, that all these elements are central in UQ of GLN. In fact, we already see that L is entries of L belongs to that subalgebra, and it turns out that these traces of powers actually generate the center of this subalgebra. No, the full algebra. For the full algebra, we need some extra simple elements. But for the subalgebra, that's exactly the generator of the center. So now what is the Harish-Chandra isomorphism in the Q version? It's defined in similar way. The only difference now, it's convenient for technical reasons to consider kind of lower triangular condition. We consider vector psi, so LQ of lambda is generated by vector psi, which is killed by a lower triangle generated LJ minus. And it's eigenvector with eigenvalues q to the lambda i's. You may think of lambda i's as integers, for example. And then again, the same as before. Every element of the center acts by scalar multiplication. And in this way, we got a Q version of the Harish-Chandra isomorphism, but formulated for the subalgebra. If you consider the center of this reflection equation subalgebra, then it's isomorphic to the algebra of symmetric polynomials in the Q variables, Q to the 2 lambda 1, Q to the 2 lambda m. So that's how it looks like, and this goes back to Joseph and Letsta, Rosso, and Tanisaki in the 90s. And notice there is a difference here in L, so there is extra shift I use here. So therefore, the first question which I want to address is, what are the Harish-Chandra images of those quantum Gelfand invariant found in 1989 paper? That question was not answered until now. For some reason, I don't know what the reason was, but here is the answer. That's our first theorem. The Harish-Chandra images are given explicitly by this formula. Now we use Q numbers. And so the same structure of the formula as for the classical case for the Perelomov-Popov formulas. So we have Q to the 12Km, and so this is just an explicit formula. In fact, when we let Q go to 1, we go back to enveloping algebra for GLN, and that way we can recover Perelomov-Popov formulas as well. So that's our first result, and as I said, the proof relies on Liouville type formula relating quantum determinant and those quantum traces. So that formula, in fact, was proved by Béliard and Ragossi for quite different motivation. They considered some beta ansatz, and they proved that formula without considering its applications for representation theory. So that's the first theorem. Now, second theorem, q-immanants. What are they and how we introduce them? So this is Hecke algebra, as Naihuan already introduced in his talk. And what I need, so-called Eutsys-Morphy elements. Yk defined as follows. Just certain elements in the Hecke algebra, k running from 1 to m. If k is 1, this is just 1. So these elements pairwise commute. This is a commuting family of elements of the Hecke algebra. So they were first introduced by Cherednik, Dieper, and James in 1987, and used to construct primitive idempotents for the Hecke algebra. So the Hecke algebra by Q is generic, is non-zero and not root of unity. In that case, the Hecke algebra is semi-simple. Direct sum of matrix algebras. Sizes of the matrices are, so f mu by f mu is the number of standard tableau of shape mu, which Naihuan explained in his talk. And the diagonal matrix units under this isomorphisms are certain elements on the right-hand side, but they correspond to certain element of the Hecke algebra, and they can be given explicitly as in terms of the generators, like TIs or Eutsys-Morphy elements. That is possible to describe explicitly. I give just a couple of examples how they look like. If your standard tableau is just column tableau like this, that the corresponding primitive idempotent is the following simple product of Eutsys-Morphy elements and Q powers. And similar formula for one row diagram and corresponding standard tableau. Then U looks as follows, but in general the formula is not much more complicated. It's the similar kind of formula which you can write EU explicitly. So the Hecke algebra acts on the tensor product of m copies of Cn by the formulas, which also recalling from Naihuan's talk. Ti goes to Rk, k plus 1. We now consider several copies of endomorphism algebra. Rk, k plus 1 means the matrix which lives in the two neighboring copies. R check explicitly looks as follows. So that is the explicit formula for the action of the Hecke algebra on this tensor product space. And here is our first result, which looks as a definition. So a definition is a result. So this guy is to define q-immanent polynomial. That's the formula which we produce as a first result. So I need to explain what this formula means. So first of all, we consider m copies of endomorphism algebra tensor by UQ of GLN and using the same subscripts as before, like L1 plus, L1 minus. These are L matrices living in the corresponding components of the endomorphism algebra. Now some combinatorial notation here. Ck of u is equal to j minus I is the content of the box alpha. So every box in the Young diagram have a row and column number ij, and we'll look at the entry k which occupies that box. Then ck of u is just the difference j minus I of the row and column numbers. That's the content of the box occupied by k in the standard tableau U. So this formula here depends on the chosen standard tableau U of shape mu, but in fact that element on the right hand side does not depend on mu. It requires a proof, but it can be shown that it only depends on Young diagram, not depending on the tableau. And the expression under trace is here. This is some polynomial in Z, and what we call it is q-immanent polynomial. And equivalently, we can rewrite this definition as follows. We can use subscripts in slightly different sense. x1 bar is x1, but starting from 2, xk bar is this conjugation by the matrices. So using this new definition, new subscripts, we can write simple formula for the same q-immanent polynomials in this way. And in this way, here L is the same matrix I introduced earlier. This formula shows that the corresponding coefficients all belong to that subalgebra, to reflection equation subalgebra, which was defined as subalgebra generated by entries of the matrix L. And it only depends on L, not L plus and L minus. That's what we see from this equivalent definition. And now comes our next theorem, which tells us that all coefficients of that polynomial belong to the center of UQ of GLN. Furthermore, we can calculate the Harishchandra images explicitly, which turns out to be factorial Schur polynomials, given by this formula here. I'll explain notation in a moment, but from that formula, we can immediately conclude that for any fixed value of z, the elements as mu of z form a basis of the center of that subalgebra here. So I'll probably need to write to explain this combinatorial notation here. So here we consider all semi-standard tableau T of shape mu. So this is Young diagram mu, and we consider T. So semi-standard tableau means that we consider all entries from 1 to n, entries in the boxes taken from 1 to n, and the entries are weakly increasing in rows, like say 1, 1, 2, and so on, but strictly increasing in columns. So this is what I mean by semi-standard tableau. So weakly increasing in rows, strictly increasing in columns. Now if we fix the box alpha, so we take ij entry. So this is box ij here. So say, oh, this is box alpha here. So if alpha is ij, the C of alpha, which I use there, is just the content of this box. C of alpha is just j minus I. And T of alpha is the content. So actually here I can write it here. T of alpha is here. So that what is used in this formula. We take the sum with respect to all such semi-standard tableau, and product is taken with respect to all boxes in this semi-standard tableau. So then we have some q polynomial, and it turns out to be symmetric in the q to the L1, q to the Ln. So that's the first result, and you may already notice one particular value of z which might be of interest. So if you take z equals 0, we will get a particularly simple formula. So the second part disappears, and we will recover just the classical Schur polynomial. So that property does not have its counterpart when q equals 1. When q equals 1, Okounkov, Olshansky factorial Schur polynomials, they always non-homogeneous. You cannot separate it. A homogeneous part. Here, there is a new phenomenon, like existence of this value, and in this way, we go to earlier work of Drinfeld and Reshetikhin. So 1989 paper, independent work of Drinfeld and Reshetikhin, they actually produced a general construction of central elements in all quantum algebras for all types. I'm talking about type A, but their formulas apply for any simple algebra. Their construction is based on the universal matrix. You need to do you need to do something with the universal matrix, take some traces, and you got certain elements for which we know that the eigenvalues, the Harry-Chandra images, are obtained by applying the character of the corresponding representation to those parameters q to the L1, q to the Ln. Just so their construction depends on the chosen finite dimensional representation of Euler algebra, call it say V, and given that V, they produce central element whose eigenvalue is the value of the character of V evaluated of those Q elements. So we know that these are exactly their element because we also know the Harry-Chandra image. The Harry-Chandra image is exactly the Schur polynomial, which is the character of our representation, and we evaluate it in those parameters. So, so in a sense, this is not a new construction because we just recover that result, but that construction is more explicit. So we have that Q traces given explicitly in terms of L operators. If mu is one column diagram, then it would be just you mean the yes. So this is precisely the classical Schur polynomial, which is the ratio of two alternants. Yes. So if that is your question. Yes. Yeah, because this variable is just different. So this is x1, x2, xn. You just substitute them for, and that you'll got the same. This is a classical Schur polynomial. So you can take any formula for them. And the second case, which is a different value of z, which is of interest from a different reason. The reason that if you substitute z, which is 1 over q minus q inverse, we got certain elements, again, belonging to the center by the theorem, and those elements can be called q-immanents. So different from those considered Naihuan, but they are elements of the center of the UQ of GLM. The reason we can call them q-immanent, because if q goes to 1, they will recover exactly Okounkov's quantum immanence. So for that reason, that we call them q-immanent, although we're a bit unfortunate that Okounkov used this terminology quantum determinant. Why did he call it quantum determinant? There is nothing quantum for GLN. So the appropriate terminology would be just non-commutative immanent, probably. But he already used quantum. So therefore, we have to say q-immanent rather than quantum. But it would be it would be right name for these elements here. Because this is a Q extension of his elements. So in fact, we also get some results about corresponding Capelli identities, which I'm not going to discuss now. In Okounkov's paper 1996, he also constructs higher Capelli identities. He shows that corresponding classical counterparts of these immanents have very nice images in differential operators, which is known as high Capelli identities. They also exist in the Q case. They are all written in our paper, but I'll not be able to discuss it now. So instead, I move to affine case. Now, what are the corresponding quantum Sugawara operators? So what are we doing here? The idea is somewhat similar to the finite dimensional case. We consider quantum affine algebra now, UQ of GLN hat, which is generated by infinitely many elements. Lij plus minus R, Lij minus R, Ij running matrix indices, R running from 0 to infinity, and invariable central element Q to the C. And the defining relations are as follows. First of all, at the zero mode, when I is 0, they are exactly the same as for the finite dimensional case. And for the remaining generators, they are written as the following real relations. So with the same meaning of subscripts as before, but this time I'm using the matrix depending on a parameter. So there was constant matrix R, now there is matrix R of U, and there are powers of Q changing from left to right. So in particular, these relations, last relation are not stable if you multiply the matrices by a scalar function. So this is the definition. This is a standard well-known definition. In this formulas, we combine the generators Lij plus minus of U into matrices. So matrix elements Lij plus, this is an expansion of non-negative powers of U, and Lij minus of U is expansion of non-positive powers of U. But in these cases, both L plus and L minus are full matrices. They are no longer triangle, they only triangle in zeroth mode. And there are, these defining relations are rather complicated to write down explicitly, but most of the time you would work with this form of relations. Their matrix, which we use there, is R of x, given by this formula. R here is the same as before, the same as we used in the finite dimensional case. R to 1 obtained by swapping the factors and replacing Q by Q minus 1, and then multiply by x. Then altogether this is multiplied by the following scalar: f of x, q minus q inverse x, when f of x is rather special formal series in x with constant of 1, which is uniquely determined by this difference equation. So it all goes back to work of Reshetikhin, Semyonov, Tanshansky, 1990, where they introduced affine algebras with central extension. And the significance of that function f of x was explained in the paper of Igor Frenkel and Nikolai Reshetikhin in 1992. So we need this extra factor for the matrix R to satisfy certain crossing symmetry condition. There is important crossing symmetry that fixes the scalar factor which we want to use here. So with all these definitions, now we'll move to the critical level. The critical level when C is minus n, that's the value of the central element. And we want to consider big algebra, as our elements are going to belong to some completion of that algebra, which I formally introduced here, U tilde of UQ of G length hat on the critical level is defined as the inverse limit of following quotients by the ideal JP, P greater than 1, when the JP is the left ideal of the enveloping algebra generated by elements Lij minus R, where R is greater or equal than P. Even though this is a left ideal, the inverse limit has a well-defined structure of associative algebra. This is a big algebra. In fact, these elements of this algebra act in a certain category of modules which similar to Slava's smooth modules. So we can see the modules which have a vector V, which is killed by sufficiently large Tij minus of R. If I is big enough, that is, they kill by all these elements. So there is a natural category of modules of this algebra to consider. So then, as with the finite dimensional case, I'll start with a standard mutable U, and we introduce the Laurent series is mu of z in z as follows. So this is also our result, because second definition is another result given by this following formula. So this time we take traces, the Q traces as before, and I use the same E capital of U. So remember that E capital of U is the image of the primitive idempotent with respect to the action of the Hecke algebra. I still use the same Hecke algebra as before, and E capital of U is the image of that primitive idempotent. Then I use L1 plus ZQ minus 2 C1 of U, Cm of U. These are the contents of the corresponding boxes in M, similar for Lm minus inverse, and there is a shift minus n here. The structure of the formula is similar to the finite dimensional case, but we have more terms here. So what we can say about this formula? First of all, it only depends on mu, not depending on the chosen standard mutable. Or we choose any one, we still get the same series. And the second property is that all coefficients belong to that completion. So think of multiplying these elements. So L plus is a series in Z where the coefficients of Z are non-negative. Then you multiply by L minus, and now coefficient of Z is negative. That's when you multiply these two series, you have infinite series of elements. But that series belongs to that completion. So that's the reason we wanted to introduce this completion, because the coefficients of the series, they belong to that larger algebra or formal series of elements. All right, and our theorem on this on Sugawara operators is as follows: all coefficients of this series are quantum Sugawara operators. What is this? By quantum Sugawara operators, we mean the elements of the center of that completed algebra. We take this completion and consider the center of the completed algebra. So all those coefficients are central in this huge algebra. That's the main result concerning Sugawara operators. So this generalizes a construction, previously known construction of Sugawara operators for non-deformed case for q equals 1. There were recent progress in constructing such operators by Chervov, Talalayev, starting in 2006. Then we work with Sasha Chervov. So there are some constructions for q equals 1, but this is a q analog of those constructions. We produce those elements explicitly. A case of one column diagram was considered before. I'll work with Naihuan and also Luc Frappa and Eric Ragassi. And in fact, again, as with the central elements for the finite dimensional case, there is a general construction due to Jing and Ettingov, 1994, of similar style. they use universal matrix, some representation of underlying algebra. They do some cooking, some expression out of this and say, yes, these are Sugawara operators. So the difference between our formulas and theirs, that our formulas are explicit. So we give those results in terms of the generators of the algebra. But morally, this was somewhat known as well. So basically, so now we come to a theorem, and in this theorem, we'll calculate the Harishchandra images. So I'll probably not be able to explain full details of that, but the definition of the Harishchandra images is more complicated but similar. We project, suppose you have a certain expression involving all matrix elements of L, and we project on the diagonal. So upper triangular and lower triangular generators disappear in certain way, and well, the projection only depends on the diagonal generators. So the formula here is of the same style as before. What I use here, the summation is taken with respect to all semi-standard mutable tau, the same way I explained on the blackboard. So we consider all semi-standard tableau with entries from 1 to n. Then C of alpha is the content of the box alpha, and this expression here is just something, certain series, which only depends on the diagonal entries, Lii plus of z and Lii minus of z calculated in this explicit way. So this formula very much reminiscent of just combinatorial expression for the Schur polynomials, but this goes to a fine level. So this is kind of a fine object given in this way. And so I'll finish by concluding remarks. So if you look carefully at this Harishchandra image, then we recognize the so-called Q character of the evaluation module of the UQ of GLN hat. So just projecting Cn to the power m by using our primitive idempotent, we got L of mu. This is a representation of UQ of GLN hat. And its Q character was, so like, first of all, Q characters were introduced by Frenkel, but different Frenkel. That's Edward Frenkel and Nikolai Reshetikhin. And then also developed in the paper by Edward Frenkel and Evgeny Mukhin. The Q characters were calculated in those papers, also paper by Brand and Kleshev. So those formulas which I just show you once again. So this formula on the right hand side, if we ignore that expression here and just reinterpret this formula as follows, that x T alpha C alpha, think of this as abstract variables. That's what is used in that theory. And in that, after that identification, we got exactly the Q characters of those evaluation modules. So that's the first remark. And the second remark is that this Harishchandra isomorphism is consistent with the action of Sugawara operators on so-called Q-deformed Wakimoto modules or at the critical level of the quantum affine algebra. They were introduced by Awata, Daki, Shiraishi in 1994. Therefore, the formulas for Q character essentially reproduce, so give us the eigenvalues of those central elements in the Q-deformed Wakimoto modules. So that's where I stop. Thank you very much.
Okay. Thank you for the talk. Have questions?
Okay, so the first remark on this slide, it's only at the critical level statement.
Yes.
So what?
Sorry. What is? So about Q character, right?
Yes. Is it at critical level or?
Yes. So this Sugawara operators, they only exist at the critical level. So away from the critical level, we don't have them. So the general theory tells us if you're away from critical level, the center is trivial. The center of the completed algebra is trivial, only consists of scalars.
But okay, maybe they're no longer center, but maybe they commute and formula still holds.
Well, you can try to use the same formulas. The formulas don't remember whether they use critical level or not, and you can say something about them, but it's formally speaking, these elements do not belong to the center. That's what I'm saying. So this is on the critical level.
Okay, let me rephrase this question. Can you define as mu away from critical level? I don't ask if they form centers. They don't, if I understand. But can you define them away from critical level? Are they just transfer matrices or something else?
Well, if you look at the definition, so the definition here is the definition. So critical level is here. It's minus n. So if you want, you replace minus n by your level, whatever you like. But what can you say about these elements? So the answer is yes, you can introduce them. There is no problem. But the question is, what do you do with them?
Well, I mean, character is the image of transfer matrices, right?
Well, maybe you can do something with them. Yes, thank you very much. Yes, maybe you can do something with them, but we don't know.
Thank you. More questions? If no, let's go for coffee break. Thank you.